This is Group 5's project proposal presentation for the underwater acoustic model for whale species by Ace, myself Fahima, Owen, and Kangvin. The problem that we strive to solve is to develop a clear and concise computational system with the ability to recognize and group whale sounds together automatically to support research and conservation efforts. Our system would be able to enable deeper insights into whale behaviors and social structures, help with identifying distributions caused by human activity, reduce labor and costs for marine researchers, and allow for early detection of possible endangered species. Many marine researchers lack a reliable automated system that can do what we plan to implement in our design: detection and interpretation. For our main model, the system begins with a physical sensing subsystem built around a marine-grade hydrophone unit capable of capturing the wide frequency ranges which characterize as whale communication. This hydrophone is paired with low-noise amplification, protective waterproof housing, and appropriate filtering electronics to ensure high-quality, distortion-free recordings, even in noisy or dynamic ocean environments. Once audio is captured, the data logging and storage module records and preserves the underwater signals at high sampling rates, allowing for multiple hour or multiple day deployments. The recorder supports standardized formats, embeds timestamps, and logs environmental metadata, ensuring that every dataset is organized and ready for analysis.
Hello, my name is Eastmore, and I will now be presenting. So, how end users would use the model are there's first of all like 6 different things that would happen with this. There's the real-time detection of whale calls, which would be what we consider most likely the main purpose of it, where researchers can upload or stream underwater audio with a product that we would put out that would automatically detect the whale vocalizations in the signal. The species would be identified uh, and by the model, and it would be labeled for different call categories, so we can understand which type of whales are present. There's the model would the processing steps in this model would allow for call separation from overlapping sounds to allow the vocalizations of the whales to be heard in even recordings that are a little bit jumbled with different noises such as boat propellers and things of that nature. The behavioral pattern of these whales would maybe be able to be deciphered from these recordings, such as mating calls, stuff of that nature. Maybe like calls from mother to child or child to mother, and other sorts. There would be the visualization of the spectrogram, which would be one of the main things that will be used during this project for training of the machine learning part. Is we are going to use spectrograms. So the visualization of that spectrogram would be just interesting to see for researchers and stuff. And then the processed calls, metadata, and model results can be organized and exported for publications and the collaboration or long-term monitoring. So as for the system overview, if you are looking at the slides, it all begins in the top right in data acquisition, where which would be from a commercially ready product that would be that researchers would use, or it could be set up in certain places specifically where it could be permanently monitored 24/7. This data acquisition would go into the pre-processing step. So this would be simple pre-processing and filtering, which would be taking the actual audio and turning it into a spectrogram and filtering out certain parts depending on what is detected in the pre-processing step. Then it would be the audio grouping and classification, where the machine learning is used to actually process or actually take a look at the spectrogram and try and detect what and classify which type of whale is there. And then this would be all output which it can be then evaluated by researchers and to detect if is this true, does this seem correct, and if it is, it can be used to just be shown to the researchers and allow them to actually identify what's going on in the region and the area. The final part is the subsystem components. The first component of the subsystem are the hydrophone, which would be, of course, the data acquisition step that would be used and then feed into what we are going to either use an Arduino or a Raspberry Pi, which would be what takes the input from the hydrophone and actually allows the machine learning or does some of the pre-processing steps, and then allows for the researchers to actually get real-time feedback and on the processing of what is going on with the data. And the third component of the system would be the actual machine learning model, which would be, of course, used in the classification step of the system overview.
Alright, I will be talking about the subsystem interface for my part of the presentation. The first part is the hydrophone and sensing. We will build a device that receives underwater sounds at pressure wave and convert them to analog electrical signal. After that, we will be building the front-end conditioning, basically the gain, basic filtering, and ADCs, in order to digitalize the system to the required sampling rate. Afterward, we will output the time-stable audio and stream to the next steps. For file conversion, we will take raw recordings from the first step in whatever format, convert it to a standard format, 24-bit WAV, apply resampling and channel formatting, as well as the attaching the metadata to the audio. We can also chunk long recordings into manageable segments. This will help with pass clean audio to the storage and classification subsystem. The next step will be involving ingesting that audio segment that we have created and storing them into a metadata and a database. We'll run detection and classification model that will be training to label segment with species, call type, and then attaching a confidence score to the result. Afterward, we will output the result in audio clip to the user interface via created API. In order to implement the interface, we also have to identify challenges that we would also be encountering while changing data. The first challenges involve high ambient noises. This is simple. When it comes to rain, boat, or other animal, we will have to filter out and make sure that recording is clear for the call detection and denoising as well. The second challenge will be coming with the large volume of long recording that require careful design of storage, indexing, and processing throughput so that the model can be trained effectively. The last challenge will be with the availability and quality of the dataset that we will be given to train the model on, whether or not the targeted species is available, and as such, model performance and channelization are hard to predict. And lastly, we'll be talking about the planned implementation for prototype. Things that we plan to implement for this prototype include a basic recording / ingest pipeline for either hydrophone setup or curated underwater audio dataset. An implementation of pre-processing script to resample audio, essentially applying bandpass filter and generating spectrogram. We will also be training an initial model on a small set of species to evaluate the accuracy of held-out calls. Lastly, we'll also be creating a simple web dashboard where the user upload audio as well as trigger analysis and view predicted species plus spectrogram.
Hello, I'm Owen and I'll continue through the rest of this presentation, starting with the project schedule and the timeline. So, starting with when we were introduced to the subject, it was around October 17th, and on the same day we had our first meeting with our sponsor, Dr. Ibrahim. I believe that's how it's pronounced. I'm sorry if I mispronounced it. But then on November 2nd, we started with the system level design, and we started doing block diagrams, state diagrams, everything that was necessary. And we established a planner on a week later, on November 9th, to have everything ready to go as a checklist and possible deadlines that we would need. It's flexible, so it allows us to finish before when the project is due. However, it's best to have those deadlines as they are. And on November 17th, we finished with our proposal draft. On November 21st, we are starting to understand the software, the signal processing, and the bobs and whistles of this project. We had our most recent sponsor meeting on December 1st. Truthfully, I didn't know what else to put, but it was important because it was able to schedule when we are going to present. And we also submitted our proposal that you are watching now and the document on Canvas as of right now. and then we'll be reviewing our peers on December 3rd between the four of us. We'll have a team summary meetings, or the team meeting summaries posted on December 7th. Then between December 28th and January 4th, we're going to begin the coding in the hardware end of it. And realistically, we should be done by February 10th to complete the model. It'll undergo either last-minute testing or be done with its testing and training, and it'll be prepared for deployment. Hopefully. This is still flexible because we wish to be able to have it complete, so worst case scenario, we can fix any last-minute mistakes. The presentation is on March 16th. We are going to be preparing for this. And as our project is supposed to be complete on May 1st, we wish to have the final checks, as appropriate, a week beforehand. So, how are we going to get this done? We have tasks assigned to each of us. Ace, for example, is going to be building a filtering and denoising step, which will also improve the signal quality before classification. Fahima has been doing amazingly with the meeting summaries and will continue to do so, but we will also include acoustic data ingestion and signal preprocessing pipeline to her challenges. For me, I will be doing coding in Python, training the model, and testing the data set that we have and the possible multiple data sets we have. Kang will be using the prototype software, the edge capture pathway, and the data I/O wrapper to complete the physical model itself. Thank you so much for paying attention to our proposal, and I'd like to end on some closing notes. The project develops an automated system to detect, classify, and separate whale calls from underwater recordings. The machine learning and clustering will be used to organize vocalizations and uncover communication patterns. The fact that this hardware is low cost doesn't really hurt us either, because it enables practical testing and a potential real-time deployment in the field in eventuality. The final system will be supporting marine research and conservation by making whale communication easier to study at scale. This will also result in being able to taking a census better. Thank you so much.